Hi, and this is our last lesson on what do you call this? Organic. And as I said before, you will often see questions where they're asking you to talk about intermolecular forces in the organic form of organic molecules. So I've combined this from different places, and I've also shared this document with you. So for learning that you have it, but I'm going to go through it very fast because you actually have it on your um, on your Google Classroom. So you will see that the first thing that we're going to look at is what type of molecules are these actually. And you should remember that these are London dispersion or just weak London, or you can call it temporary dipole or induced dipole forces, whatever you've been used to calling it. Because if you look at the normal hydrocarbons, it's just an organic molecule that looks like this. And what normally is the case is that they're basically symmetrical. Not perfectly symmetrical always, but for the most of it, they are forming symmetrical molecules, which means that they are non-polar. And as soon as they are non-polar molecules, then you must know that they will always have London forces between its molecules. So these ones are weak and they are normally gases. And you know that it's methane gas, ethane gas. Those are the gases that we work with in the lab, actually. Then when you look at the haloalkanes, the haloalkanes or even the esters, if you look at a haloalkane, it would be something like this, where I now have a Br here. So if you look at that molecule, it's got hydrogens everywhere, but here I have a bromine with a higher electronegativity and also some lone electrons. So this side of the molecule will definitely be a little bit delta negative, and this side will be positive. So therefore, this is a polar molecule. And if it's a polar molecule that does not have hydrogen bonding, then we know that it is going to be dipole-dipole forces. The same with an ester. You can see that from, if I draw an ester quickly for you, hopefully by now you know the homologous series and you know the functional groups. So for an ester, you should know by now that we're going to have a double bonded O, then we're going to have an O, and then we have the carbon chain carrying on for ever long. But here again, we have the O with its lone electrons and also high electronegativity towards those two shared pairs. So therefore, this side where the O is, again, will be delta negative. Remember, this is a flexible molecule. It doesn't necessarily form a straight line like this. But that side where the oxygen is will then be delta negative, again making it a polar molecule and giving us a dipole-dipole intermolecular force. The last two are for hydrogen bonding. Remember, it's also an intermolecular force. It's not to do with the atoms, but the atoms inside is to do with the molecules. So for an alcohol, you will have an OH. Now remember, if you've got an O and an H here, so what you need to focus on is that OH that you have there. So the molecule here have an O and an H, which means that here there's a hydrogen bond. So, or it's going to cause a hydrogen bond because this side is going to then be delta positive. And if I have that exact same molecule, it's going to be attracted to the delta negative of the other molecule. That one's OH will be on this side. It will be the delta negative. And the hydrogen bond, remember, is there between the two molecules, not between the O and the H, it's between the two molecules. So that's my hydrogen bond. And please, I don't want you to just say hydrogen bond. I want you to say hydrogen bond intermolecular force. The same for a carboxylic acid. Carboxylic acids also have an OH. So you know the carboxylic acid by now. You will then draw a carboxylic acid like this, and you will have a carbon and a carbon. You will have a double bonded O on one of your carbons, but then the molecule will end in an OH. So again, you have a OH there that is a hydrogen bond, and it is going to form a dipole-dipole. So there's actually two things. There are more complicated reasons why carboxylic acids are stronger than alcohols, but we don't go into lots of detail in a matric, but up to matric because we don't need to. And then, so if you can see that there's a hydrogen bond there, and it's a dipole-dipole because of this is going to be not a symmetrical molecule, it's a polar molecule already. So there could be something happening. So here, actually, we can have a H of another molecule that would then be the same type of molecule than the one we have at the bottom. So if I draw this now nicely, you will see that this would be my delta positive of this molecule attracted to the delta negative of this molecule. And if you look at this molecule here, that side is the delta negative, and here where we have the H is going to be the delta positive that can again go to another molecule's delta negative. So the intermolecular force, the hydrogen bond intermolecular force is again there between the two molecules, not there, between the two molecules. That's our intermolecular force. So this is a nice diagram to show you that if the difference in the strength of the intermolecular forces going all the way from symmetrical molecules to carboxylic acids. Then the next thing we look at is the amount. If I give you two molecules to compare and they both alcohols or they both the same thing, then you're going to look at the number of functional groups. So you can see this one only have one OH or one hydroxyl group. This one has two hydroxyl groups and this one has three hydroxyl groups. So this one can form one hydrogen bond, this one can form two hydrogen bonds, and this one can form three, or actually four because it can form it on the other side of the molecule. But you can clearly see that the number of functional groups increase and therefore the strength of the intermolecular force will increase. And then I've given you the steps in the notes nicely how to answer. Because the intermolecular forces are greater, there is more energy needed to overcome the forces, therefore higher boiling point or whatever the question is asking you. The chain length is very important. Actually, not so much about the chain length than it is about the number of electrons. Because remember when we did London forces, when you looked at these molecules, there is only a certain amount of electrons. There are a certain amount of electrons, but as the chain gets longer, the number of electrons will increase. If I have more electrons, remember they are moving around at the speed of the light around the molecule. If there are more electrons, there are a bigger chance of temporary dipoles forming so that the electrons can be on the one side of that molecule. So if a temporary dipole forms, like we discussed in London forces when we discussed that, we have a stronger and more temporary dipole, so therefore the induced dipoles are going to be stronger and more, and therefore we're going to have an increased intermolecular force, which in this case would be London intermolecular forces. But because there are more electrons, there are more chances of temporary dipoles forming and stronger ones, and I've given you the points again in the notes how to specifically answer, almost like a little recipe. And then the last one is if you have a straight chain compared to a branch chain. Now these ones have got exactly the same molecular formula. So you will see they all have 5 carbons. So they all C5. H double plus 2 will be 10 plus 2 is 12. So you will see that they all have this molecular formula. So we can't say that one has more electrons. And they're all single bonds. But if you look at this one, there's a big surface area. This one has basically come in to that position and it's got a smaller surface area. It's almost like a circle having a ball having less surface area than a square. And then this one has the least amount of surface area. So again, these are weak London forces. So these are for all three of those molecules, you're going to have London intermolecular forces. And these London intermolecular forces will increase in strength because there is more space, more surface area for temporary dipoles to set up. So again, because there's more temporary dipoles and therefore more induced dipoles, I have a stronger intermolecular force, and therefore I'm going to need more energy to break these or overcome these intermolecular forces, and giving me then, you know, energy needed, giving me an increased boiling point and melting point. You can't write boiling points and melting point. So make sure that you can follow those steps. Most of these questions are 3 or 4 marks. They will give you 2 of these molecules and say, explain why this one has, for instance, a lower boiling point than that one. Or they can say, why is this one a gas at room temperature and that one is solid? And then you go through the steps as we did in intermolecular forces. And you just explain that step by step. And that is it. So the only lesson I have left is the what do you call it? The summary on the organic molecules. And for that, you're going to need that last page in your notes. But I'll show you nicely. So one more lesson from me, and then it's time for your Ciabula exercise. Please don't forget that. It is only due at the end of the holidays, but you need to do it. It's not going to be on organic, it's going to be on